Hello, everyone. Today we're going to discuss Newton's third law of motion. This is the Chapter 5 material, and we'll be going through it in two parts. The first thing I want to mention, and this is shown on slide 2, the bullet points, is that the third law of Newton's third law will be discussed in some detail, how it relates to vectors and forces and interactions, and then we will do a summary of Newton's three laws of motion. I would like to say that in regards to the third law, since we're starting it off, it's good to discuss and mention up front exactly what that is. Newton's third law of motion says in very short terms, for every action there is an equal and opposite reaction. To expound on that a little bit further, we can say that if an object A exerts a force on object B, then object B will exert an equal and opposite force on object A. And it really doesn't matter which we call the action and which we call the reaction. They occur in pairs, and so we could look at it from either point of view, whether we call it action or reaction. Simple example, if you're playing billiards and the cue ball hits the 8 ball and the 8 ball it carries away the energy or the velocity of the cue ball, then we can say that at impact the cue ball exerts a force on the 8 ball, which causes it to accelerate and move away. At the same time, the 8 ball exerts an opposite force on the cue ball, which causes it to stop on the table. So there are many examples of this, and we will discuss them further as we go through, and I'll pick up on slide number 3 in just a moment. Now, in this slide, we see a man pressing his hand against a wall. The way we describe Newton's third law in this example is that as the man pushes on the wall with some force, the wall pushes back on the man, and those forces are equal and opposite. The reason, of course, that the man does not move is because of friction with his feet on the floor. Keeps him from being pushed away from the wall, and therefore there is no motion in this particular example. When we look at the next slide, we'll see another case where Newton's third law is being applied. Okay, on this slide, labeled Newton's third law of motion, we see an example of a hammer hitting a spike or nail into the ground. And at the point of contact or moment of impact, the sledgehammer is exerting a downward force on the nail or the spike, and at the same time, an equal and opposite force is applied onto the sledgehammer from the nail. So the sledgehammer exerts the downward force on the nail, and the nail exerts the upward force on the sledgehammer. And these two are equal and opposite and give an example of Newton's third law of motion. On this example, where we have a case of a soccer player kicking a ball, we assume that the foot of the soccer player imparts a force of 1,500 newtons to the ball, and you recall that 1 newton, or I should say 1 pound, is about 4.5 newtons. So, roughly speaking, this would be about 300. This would be about 300 pounds of force. The question comes about is that when the ball, because of the fact that the foot imparts a force of 1,500 newtons to the ball, what will be the ball's reaction force against the player's foot. Now, based on our previous discussion, hopefully it'll be clear to you that the answer is B, that it must be 1500 newtons, because Newton's third law says that the force is equal and opposite to the applied force, which is the force of the foot on the ball. Therefore, the ball exerts an equal and opposite force on the player's foot. Okay, a couple things to remember about Newton's third law is that the forces always occur in pairs. It always occurs when one object applies a force to another object, and that latter object then imparts an equal and opposite force to the first object. So if object A imparts a force of 100 newtons to object B, then object B will impart 100 newtons of force onto object A. And they always occur in pairs, and it doesn't matter which one we call the action and which one we call the reaction, but it's true that they always act on different objects. As we said earlier, Newton's third law can be expressed by saying to every action there is always an opposed or opposite reaction. That is to say that the reaction occurs in the opposite direction as the initial action, and they always occur on two different objects. So in this example, we have the car with the tires turning on the pavement. As the tires begin to rotate, the tire exerts a backwards force on the road, and the road exerts a forward force of equal and opposite strength to the tire, therefore causing the car to accelerate or move forward. Another example of this would be a pedestrian walking on the surface of a street, and as the pedestrian pushes their back foot away to give them momentum, then that force of the shoe or the foot onto the pavement is the force on the pavement in the rear direction of the traveler, and therefore the pavement exerts a forward force on the shoe of the pedestrian, and this force will be equal and opposite. Thus, the pedestrian can move or accelerate by pushing their foot against the road, and the road exerts the force on the foot, causing the pedestrian to move forward. In this example, we have a rocket ship that is moving in the forward direction as a result of combustible gas that has been released by kinetic energy of its explosion. The gas consists of molecules that are rapidly expanding, and the gas molecules at the time of explosion, which of course in this case is a continuous process, since the combustion is continuously ignited in the rear of the rocket, the kinetic motion of the gas molecules, or their velocity, bounces or hits the rear chamber of the rocket ship, and that gas molecules, when they hit the wall of the back wall of the rocket, impart a force to the rocket, and that is shown by the red arrow that is accelerating the rocket to the right in the diagram. At the same time, the kinetic energy of those molecules as it hits the rear wall of the rocket gets bounced back or reflected or imparts its as a result of hitting the wall of the rocket exerts a force on those gas molecules or that fluid, I guess they should say the liquid or the gas fuel of the rocket, and that those molecules of the fuel are being repelled by the wall. That is to say, the rear wall of the rocket exerts a force on the molecules, forcing them to exit in the rear direction. So in this case, the gas fuel exerts the force on the rocket because of its rapid kinetic energy from the explosion of the gas in the chamber, causing these gas molecules to hit the wall of the rocket, the rear wall of the rocket, pushing in the forward direction. At the same time, the rear wall of the rocket imparts a force onto those molecules that hit it and send them backwards out into the exhaust behind the rocket. So the red arrow to the left indicates the force of the force of the rocket on the gas molecules, pushing them opposite the direction from which the rocket is moving, and the gas molecules hitting the rear wall of the rocket, are causing the rocket to accelerate in the forward direction. And as you can see, those arrows are equal and opposite, and therefore this satisfies Newton's third law of motion. In this example, we imagine that you are stepping off of a curb onto the street at a lower elevation, and what we know in this example is that the force of gravity, which is the Earth's mass, is pulling you down onto the street. And the question now asks the question of what is the reaction to this force of gravity that the Earth is applying to you as you step from a higher elevation to a lower elevation. Obviously, gravity is pulling you to the lower elevation, but the question is, what is the effect of the Earth in terms of the reaction? If the action is that the Earth is pulling you downward, then what is the reaction for this force? And in this case, the reaction is that the human, which in this case is yourself, is in fact also exerting a force on the Earth. And therefore, in a very almost insignificant way, we could say, you are pulling the Earth upward towards you. Now, of course, because your mass is so much lower than the Earth, then in fact, the Earth has an imperceptible amount of motion as a result of being pulled towards your mass. But nevertheless, there is an equal and opposite reaction occurring. Another way that may be hopefully clearer, if instead of you stepping off the curb, you drop a ball off a cliff. And the ball begins to accelerate because the force of gravity is pulling the ball down into the ravine or the gorge at the bottom, the valley at the bottom. But at the same time, even while the ball is in free fall, the ball does exert an almost imperceptible force of gravity, as we could say, due to the mass of the ball. So the mass of the ball exerts a force on the Earth, causing the Earth to move towards the ball. Now, this is, as we said, imperceptible because the mass of the ball is so minuscule compared to the mass of the Earth. But nevertheless, that is the reaction force, and the reaction force is that you are pulling the Earth towards you, or in this case, towards the ball. Now in this slide, slide 12, we give an explanation of why we don't sense the Earth moving towards you. I described this in the previous slide, that in fact the force of the Earth towards your body is so small because your mass is so small that you don't. It's imperceptible and nearly impossible to measure. Nevertheless, we know from Newton's third law that if the Earth exerts a force of gravity on you as you step off the curb, then the then the then your body is also exerting an equal and opposite force of attraction of the Earth towards you, which would cause the Earth to move towards you, but only in an imperceptible amount because your mass is so tiny compared to the mass of the Earth. The places where we do see the effect more dramatically would be, for example, in a binary star system. There are two stars of equal masses. They are rotating around each other. They have an equal and opposite force of gravity holding them in their orbits. They rotate around each other at the same frequency and experience the same force that holds them or binds them together. But the first star exerting the force of gravity on the second star will be equal and opposite to the force on the first star due to the second. In this slide, we combine Newton's third law with Newton's second law to examine what happens when a cannon is fired, or a cannonball is fired from a cannon. And we apply the Newton's third law of motion by saying that at the time of the explosion or the triggering of the cannonball, the explosion in the chamber that propels the ball out of the nozzle of the cannon, that there is a equal and opposite force of the ball on the cannonball on the cannon itself. So while the cannon will exhibit a force on the ball pushing it out, the cannon will recoil in the backward direction if it's not held fixed onto the earth or the floor of the from which it's being fired. We can also say at the same time that because the force of the action and reaction are the same, that the cannonball will have enormously higher amount of acceleration because the mass of the cannonball is extremely small compared to the mass of the cannon itself, and therefore the cannonball will have a much higher acceleration because acceleration is force divided by mass. Since the forces are the same in the two cases, namely to say that the force that the cannon exerts on the ball is the same as the force that the ball exerts on the cannon, then we can show with the acceleration equation, acceleration equals force over mass, that the cannonball will in fact have a much larger acceleration because of its much smaller mass. Now I'm going to let you answer the next three questions on your own. We've sort of covered this material, so you should be good to go. I'm going to put a long pause for you to read this slide, and then there will be 30-second pauses for all the other slides until we resume after the following three questions.